Moving on, unsupervised learning tackles a different yet equally crucial set of problems. Unlike supervised learning, this approach deals with unlabeled data, meaning the algorithm is given raw input without any pre-existing correct answers or outputs. It's like being handed a box of assorted items and asked to organize them without any prior instructions on what categories exist or what each item is. The core objective here is for the algorithm to discover inherent structures, patterns, or relationships within the data entirely on its own. It's about finding hidden insights that might not be obvious to a human observer. One prominent application is clustering, where the algorithm groups similar data points together based on their intrinsic properties. For example, a retail company might use clustering to segment its customer base into distinct groups with similar purchasing behaviors, allowing for targeted marketing strategies. Another key area is dimensionality reduction, which simplifies complex datasets by reducing the number of features or variables while retaining most of the important information. This is particularly useful for visualizing high-dimensional data or speeding up other machine learning algorithms. Unsupervised learning is powerful for exploratory data analysis, anomaly detection, and when labeled data is scarce or expensive to obtain, providing a flexible tool for understanding the unknown. Finally, we arrive at reinforcement learning, a fascinating and dynamic category inspired by behavioral psychology. Here, an agent learns to make decisions by interacting with an environment. There are no labeled data sets to train on. Instead, the agent receives rewards for desirable actions and penalties for undesirable ones. It's a trial and error process, much like how a child learns to ride a bicycle or an animal learns to navigate its surroundings. The agent's objective is to maximize its cumulative reward over time, developing a policy or strategy for optimal behavior. Think of DeepMind's AlphaGo, which learned to defeat the world's best Go players by playing millions of games against itself, iteratively improving its strategy based on wins and losses. In robotics, reinforcement learning allows robots to learn complex motor skills, such as walking or grasping objects, by experimenting in a physical or simulated environment and receiving feedback. This approach excels in dynamic environments where optimal actions are not known beforehand and must be discovered through interaction. From autonomous vehicles navigating traffic to optimizing resource allocation in data centers, reinforcement learning is pushing the boundaries of what intelligent systems can achieve. These three categories, supervised, unsupervised, and reinforcement learning, represent the fundamental paradigms driving today's AI revolution.